Hello friends, welcome to Electrical Engineer Convention. So today we are going to see the fourth video on the block diagrams or the architectures in communication. So this is the fourth one. So today we are going to see about the digital communication architecture. So this is the basic building block of digital communication. So let's get into it. So here what we have is we have the source signal, and the source signal, we are giving the source signal to ADC. ADC, as you all know, it is the analog to digital converter, and from ADC it goes on to sampling and quantizer, sampler and quantizer. These two blocks are together called as the source encoder, and from the source encoder it goes to the channel encoder, and from the channel encoder it goes to digital modulation block, and from digital modulation block it goes on to RF transmitter block. RF transmitter block, please refer to the third video that we posted, which is the RF transceiver block diagram architecture. So as you all know, the communication works with respect to multiple architectures. So in this case it means that the digital communication architecture works with the RF architecture. So if you see, this is the transmitter block of a digital communication system, and its input is given as its output is given as the input to the RF transmitter block, and from RF transmitter block it goes on to the channel, and from the channel it goes on to the RF receiver block, and from the RF receiver block the output is given to the digital modulation block. So we are going to undo everything that we did on the TX in the RX, like any system. So we did modulation, so we are going to do a demodulation. We did a channel encoding, we are going to do a channel decoding here. So here we did source encoding, so we are going to do the source decoding here, and we converted analog to digital, and here we are going to convert digital to analog, and finally we'll get the desired signal that we sent. So this is the output signal. Now let's see every single block in detail. So the first thing is the sampler. The sampler is nothing but it is a block that converts a continuous time signal into discrete time signal. And quantizer is nothing but it maps a large input signal into a smaller output signals, which means that it clubs a lot of signals together and makes streams of, or like it makes like codes of multiple smaller output signals. So you can also call it rounding or truncating. Rounding meaning it is assumed to be either the higher value or the lower value depending on how close it is, or truncating meaning we are just cutting it off so that it matches our output signal. We will see the quantizer in detail and the sampling theorem in detail in the next coming videos. So the purpose that we achieve with both sampler and encoder is nothing but the source coder. What it does is it does data compression. So we are converting a large input signal. Let's say we are having a large number of bits, and we are reducing it into just 8 different sets of information, or 8 is an arbitrary number, I'm just saying 8. So for example, let's say if you are having 0 0 0 0 1 0 0 1 0 1 1, some random numbers. So what we'll do is we'll group 4 bits together to represent a certain value. So if there are 4 zeros, let's assume that it is called as 1, and if it is 0 1 0 0, which means that 5, something like that, or this could be 11 or something like that. So what we are going to do is we are going to convert a large number of bit stream into smaller streams using the source encoder. This is very similar to this but not exactly the same. I'm just giving this example for the understanding purpose. And finally, and before that, after compressing the data, we are giving the output to the channel encoder. The channel encoder, what it does is, it implements the error control mechanism that we have in order to negate the channel effects. So as you all know, when we transmit a signal through a channel meaning multiple things, so in an RF perspective, it is open space. It is open space, or the air, the medium in which that we communicate. So this channel, when we are transmitting some data, let's say we are transmitting 0 and 1 into the channel, and because of the noise that is inherent in the channel, we might receive it as 1 1 instead of 0 1. So this type of error should be rectified, or the system should be able to recognize what it has sent in order to rectify what digit it has missed. So what we have to do is, in the channel encoder, we will implement error control mechanisms in order to escape from this channel errors. And finally, modulation. Modulation, as we all know, it is a technique where we modulate or change the periodic properties of the carrier wave. So what we do is, we take the message signal, and mix it to a carrier, So how do we mix it? That depends upon multiple things. So we can either change the amplitude of the signal, or we can either change the phase of the signal, or we can also change the frequency of the signal with respect to the input signals. We'll see about the digital modulation and the types of the digital modulations that we have in detail in the next coming videos, where we explain specifically about modulation. So after doing all these steps, what we have to do is, we are sending it through the RF blocks, we are sending it to the channel, we are receiving them, and after receiving them, we have to demodulate. That is, whichever we have to separate out the carrier frequency that we sent them, and we have to recover the message signal. So after demodulation, what you get is the message signal, and this message signal is not the same as that of the source. Remember that we have already encoded, we have already source coded and channel coded, which means we have done a whole lot of encoding here. So we need to decode it in order to get the output message. So what we'll do is, we'll do a channel decoder. So after channel decoder, the error correction is removed, error correction free. So after that, we are sending it through the source decoder. As you all already know, the source encoder, what it does is, it maps a large input signal into a smaller output signal. So we are unmapping it, and recovering the initial signal, which is discrete, right? So what the sampling does, it converts the time signal into discrete time signals, right? Continuous time to discrete time. So we have a discrete output here, and we pass this discrete output into the DAC. DAC is nothing but what? Digital to analog converter. So finally we have an analog signal. So you are sending an analog signal, it goes on through multiple digital modulation processes, digital modulation techniques, and it goes on to the RF architecture. And after going through the channel, it gets faded, or it experiences some loss because of the noise in the system, and it goes on through the RF receiver through the antenna, and from there it goes on to demodulation and the decoding techniques, and finally the digital signal is converted into the actual analog signal. So this is the basics of the digital communication architecture. On the upcoming videos, we will see in detail about what sampling is, what is quantization, and what are the types of channel modulation, channel encoding, and what are the different types of channel fading or channel loss that we experience. We will see all those things in detail in the next coming videos. So this is the basics of the digital communication architecture. Please feel free to ask any questions on the comments, and if you like the video, please like it and share it. Thank you.